Hi and welcome to Chemistry Video 1.3 Phases of Matter. By the end of this video, you should be able to classify matter as either a solid, liquid, or gas. You should also be able to identify the phase changes and determine whether they require or release heat. Lastly, you should be able to label and explain phase change diagrams. So let's look at solids first. Solids contain definite shape and definite volume. So what this means is that a computer on Earth will look the same even in Jupiter. It also means that they would take the same amount of space. Solids are also always in constant vibration, so if you're able to shrink yourself down to the size of a molecule and you put yourself on top of a solid, you would actually be vibrating with it. Lastly, you need to know that molecules are packed tightly together in a geometric crystalline structure. So what this means is that if you're able to take a small sample size of a solid and you place it under a microscope, it would form these boxy shapes like this. Next we have liquids. Liquids have no definite shape, but have definite volume. So what this means is that they take the shape of any container and they actually remain with the exact same amount of volume. Next, liquids are always in constant motion. So the difference between a solid and a liquid is that the liquid molecules are actually able to move around freely. There's no fixed arrangement. Finally, we can conclude that the molecules within a liquid are less compact than that of a solid, but they're more compact than that of a gas. Next, let's talk about gases. Gases contain no definite shape and no definite volume, so they're able to take the shape of any container they want. They also have no fixed arrangement, so this means is that gas particles are able to compress or they're able to spread out freely. So when we look at these phase diagrams here, hopefully you can see the difference now. When looking at the solids, you can see that they're neatly compressed. When looking at the liquid diagram, you can see that there's a little bit more room for them to move around. Finally, when we compare that to the gas diagram, you can see that they're constantly moving because when you look at these lines right here, this means that they're in random motion. Speaking of gas molecules, let's talk about the pressure that they exert. See, gases are constantly moving in random motion and exerting pressure. Now we know that they are exerting pressure because, see, in a vacuum such as space, there's no molecules. And because there's no molecules, there's no pressure being exerted. What this means is that in space, you're able to float. And you're able to float because there's no molecules that are there to push you back down. In fact, the higher up you go, the less oxygen you have because the molecules begin to decrease. Now, gas pressure can actually be measured in kilopascals or atmospheric pressure, ATM. Alright, so let's go ahead and move on to vapor. So what is vapor? Well, vapors are the gaseous form of a substance that is normally a liquid or solid at room temperature. What this means is that you can vaporize liquid, which is just turning it into a gas. You can also do the same thing for solid. You can vaporize a solid and turn it into a gas as well. So basically, vapor is simply a gas. Now, vapor is not a forced state of matter, so don't get the two confused. Alright, let's talk about an exothermic and endothermic reactions. So, first off, you should know that these are just heat transfers from areas high concentration to areas of low concentration. So the way that it works is if it's endothermic, you're going to be putting heat into the system. Now, if it's exothermic, you're going to be taking heat or releasing heat from the system. So let's go ahead and go through some practice problems. So the first one we have is evaporation. So if we're talking about evaporation, we need to be putting energy into the system in order to cause the liquid to become a gas. Therefore, this is an example of an endothermic reaction. Next, we have condensation. In condensation, what we're really doing is turning a gas to a liquid. And in order to do this, this must be an exothermic reaction. So we're getting it colder. Next, we have melting. And we do this in everyday life. So if I'm eating an ice cream outside, what do I really need to do? Well, the sun needs to put an energy into the ice cream, and by doing that, this is causing it to melt. So this is just an endothermic reaction. Next, we have freezing. Well, freezing is simply the opposite of melting. Therefore, I could say that this is probably going to be an exothermic reaction. Next, we have sublimation. So if you don't know what sublimation is, well, all it is turning a solid to a gas. And in order to turn a solid straight to a gas, we must be putting energy into the system. So this is just an endothermic reaction. Lastly, we have deposition. Deposition is simply the opposite of sublimation. This is when we're going from a gas straight to a solid. In order to do this, the system must be losing energy, and because of this, this is just exothermic. So you should also be able to describe the following. The first one being your melting point. Your melting point is the temperature change that it takes to go from a solid to a liquid. Next, you have your boiling point. This is the temperature change it takes to go from a liquid to a gas. Your freezing point is the temperature it takes to go from a liquid to a solid. So when you think about it, your freezing point and your melting point have the same temperature change that's required to change phases. They're just going to be in opposite directions. For instance, your freezing point of water is at 0 degrees Celsius, but your melting point is also going to be at 0 degrees Celsius as well. They're just in opposite directions. Next, let's talk about thermochemistry. Thermochemistry is the study of energy changes that occur in a chemical reaction. Your first one being kinetic energy. Now, kinetic energy refers to the energy of motion. So the more something is moving, or the higher the temperature, the more kinetic energy it's going to have. Next, we have potential energy. Potential energy refers to the energy that's being stored. For instance, all of you guys have a high potential energy to get an A in my classroom. Next, let's talk about the phase change diagrams. The first one being heating curves. Now, heating curves work like this. Let's just say that you take a solid and you place it on a hot plate. Well, once it's on a hot plate, what's going to happen is it's going to increase its temperature. As it's increasing its temperature, it's going to undergo a phase change. And this phase change is your first one, where it's turning from a solid into a liquid. Next, we have another phase change occurring right here. This is occurring when you're taking your liquid and turning it to a steam right here. So some common questions that you're probably going to be asked are, where is your kinetic energy increasing? Your kinetic energy is increasing wherever you're increasing your temperature. So in that case, I can say my kinetic energy is increasing right here, and right here. How do I know that? Well, my temperature is showing me that I'm increasing at those areas there. The next question says, where is your potential energy increasing? Well, your potential energy is increasing as you move across on the x-axis. So as you look right here, my potential energy is increasing here and right here as well. Next, it says, where's your kinetic energy stable? Well, your kinetic energy is stable wherever your potential energy is occurring. So my kinetic energy must be stable right here and also right here. The final question is asking, where's your melting and boiling points? Well, in order to really understand this, let's ask ourselves, what does melting point mean? Melting point is the temperature change that it takes to go from a solid to a liquid. So I could say that my melting point, therefore, is occurring at 0 degrees Celsius right here. The boiling point, on the other hand, is the temperature it takes to go from a liquid to a gas. So because of that, I can say that if this is a liquid and this is a gas, the temperature change that's needed to go from here to here must be right here, which is at 100 degrees Celsius. Alright, so here's another phase change diagram. It's probably best if you pause the video and try these by yourself. So for number 1, it's asking, which line segment represents a liquid? So in order to answer this, you have to make the assumption that your starting point is going to be your solid phase. In this case, it's point A. So point A is right here. I'm undergoing a phase change, and therefore, my liquid phase must be occurring at point C and D. Next, it reads, what is the boiling point? Well, the boiling point is occurring right here at 95 degrees Celsius. And I know that because the boiling point is the temperature change that it takes to go from a liquid to a gas. Next, it reads, what is the freezing point? Well, the freezing point, we can do this by reverse engineering and working our way backwards. In this case, I can look at my phase change and I know that this is where a liquid's starting to occur. So in order to go from a liquid to a solid, it must be at temperature 55 degrees right there. So for question 4, it reads, on what line segments is the potential energies increasing? Well, potential energy is increasing on that x-axis right here from point B to C, but also on point D to E. Lastly, it's reading, where is your solid and liquid equilibrium? In order to answer this, you need to understand what equilibrium means first. Equilibrium is when two things are at equal temperatures. So in this case, all I have to find is the solid and liquid phase change, and then I can make that point my temperature change. First, I gotta find my solid phase, and then my liquid phase, and then I can say that point B and C is probably going to be that phase change where they're at equilibrium temperatures. Alright, so let's move on to the next phase change diagram. This is your cooling curves. Now your cooling curves are exactly like your phase change diagrams for heating curves, except now it's working in the reverse order. So at point A, this must be that we have a gas. At point C, we have our liquid, and then at point E, we're going to have our solid phase right there. So where's your kinetic energy decreasing? Well, our kinetic energy is decreasing as we decrease our temperature. So from point A to point B, we're going to be decreasing our kinetic energy. And then at point C and D, we're also going to be decreasing our kinetic energy. And then finally, from point E to F, we're having a decrease in kinetic energy. So the next question reads, where's your potential energy stable? Your potential energy is stable wherever your kinetic energies are occurring. So in that case, I can say that my potential energy is going to be stable right over here. Also, it's going to be stable right over here and here. So the last question is asking us, where are melting and boiling points? So our boiling points are occurring where the temperature is going from a liquid to a gas. Therefore, I can say that it's from point B to C. Next, to determine the melting point, we need to understand this is where it takes to go from a solid to a liquid. In that case, it's just going to be your point D and E right over here. So by now, you should be able to classify matter as a solid, liquid, or gas. You should also be able to identify the phase changes and determine whether they require or release heat. Lastly, you should be able to label and explain phase change diagrams. Thank you, and I'll see you in chemistry video 1.4.